Welcome back to the Deep Dive. Today we're tackling something that honestly feels a bit like science fiction, but it's becoming absolutely critical for our climate future.
Yeah, we're talking about actually pulling carbon dioxide straight out of the air.
Direct air capture, or DAC.
Exactly. And, the idea itself isn't brand new, but scaling it up, making it work on a level that really makes a difference. That's a huge technical and maybe even more an economic puzzle.
Can it actually be done? And
Mm.
can we afford it? That's the core question. And to explore that, we're diving deep into a really important piece of research today.
Mm-hmm.
It's the study titled Techno Economic Assessment of CO2 Direct Air Capture Plants.
And this isn't just a quick overview. This study, it really gets into the weeds, comparing the different technologies, figuring out the costs, the challenges, and, the role DSE might actually play in hitting those climate targets we've set.
So our mission today is to unpack what this study found. What happens when you put these DAC ideas under a serious techno-economic microscope? What does it tell us about making this a real-world solution?
Let's get into it.
Okay, first, let's just quickly set the scene. The problem. We all know the background. CO2 levels way up from pre-industrial times, right? Around 280 parts per million, and now over 400 ppm.
Yeah, a huge jump. And we have the Paris Agreement aiming to keep warming well below 2 degrees Celsius, preferably aiming for 1.5.
And this study, like a lot of the recent science, is pretty clear.
Mhm.
Just cutting our current emissions, even drastically,
Mhm.
it's probably not going to be enough on its own.
Absolutely fundamental. Cutting emissions is step 1, 2, and 3. But we also need ways to actively pull past emissions out of the air. Negative emissions technologies, or NETs. That's where DLE fits in.
Okay, but hold on. There are other ways to deal with CO2, right? What about capturing it at the source or planting trees? What does this study say about those?
Good point. The paper does touch on those. Point source capture, PSCC, grabbing CO2 from power plants or cement factories, super important for reducing ongoing emissions. But this study points out limitations. It never captures 100%, typically more like 50 to maybe 94%. And it just can't touch distributed sources like all our cars and planes. Plus, you can't always retrofit old plants.
Right. And the natural solutions. Trees, bioenergy with capture.
Also part of the mix. But this study highlights the potential downsides if we rely only on those at a massive scale. We're talking huge land requirements.
Competing with food, biodiversity.
Exactly. Water use, food security, biodiversity. These are real concerns mentioned in the study. Even things like enhanced weathering, another net idea, could mess with ocean chemistry if done carelessly. They have a role, but they aren't the complete answer.
So that brings us back to DC. And the big advantage this study emphasizes is its flexibility.
That's the key takeaway. DC can capture CO2 from anywhere. It doesn't matter where the CO2 came from originally.
Ah, okay. So it can tackle those legacy emissions, the historical stuff already up there, and also the hard-to-abate sectors.
Precisely. This study argues that DSC, deployed at scale alongside those aggressive emission cuts, is pretty much essential if we want to stabilize the climate.
Right, so we need it. What is it, fundamentally? This study seems to break it down into two main flavors based on energy use.
Yeah, they categorize them mainly by the temperature needed to release the CO2 once you've captured it. So you have high temperature aqueous solutions, HTDSC.
And low temperature solid sorbent, LTDSC.
Correct. High temp versus low temp. That's the big dividing line from an energy systems view.
Okay, let's unpack those a bit. High temperature first. How does that work?
So with HTDSC, you're usually using a liquid, an aqueous solution. Think of things like sodium hydroxide or potassium hydroxide solutions. Air flows through this liquid, and the CO2 gets absorbed, chemically reacting.
It gets captured in the liquid. Then what?
Then you need to get that CO2 back out in a pure form and critically regenerate the original liquid so you can reuse it. And this study explains that this regeneration step, well, it needs serious heat, like 900 degrees Celsius.
900 C. Wow. That's
Really
furnace
hot.
territory.
Pretty much. Often done in something called a calciner or kiln. The paper even details the chemical reactions, which, shows they really dug into the process specifics.
Okay, so HTDA equals high heat demand. What about the low temperature, LTDAC?
Right, LTDAC uses solid materials instead of liquids. These are called sorbents. Air passes over filters or structures coated with this stuff, and the CO2 sticks to the surface. That's adsorption.
6 at normal air temperature?
Yeah, ambient temps. And the key difference, like the name says, is getting it back off. You don't need 900 degrees. It's much lower, typically in the range of 80 to 100 Celsius.
Okay, that's a huge difference. Still hot, like, very hot water, but not a furnace. How do they generate that heat?
usually with steam or just hot air, sometimes helped along by pulling a vacuum, much less energy intensive on the heat side.
And does that translate directly to overall energy use? Less heat, less energy?
Generally, yes, especially for thermal energy. This study looks at data from earlier work suggesting HDDA needed, maybe 1,400 to over 2,200 kilowatt hours of heat per ton of CO2. Yeah, and often more electricity, too. LTD numbers were lower for heat, maybe 1,100 to 2,000 kilowatt hours per ton, and often less electricity as well, though it really depends on the specific material and how cleverly you reuse heat within the system.
So these basic ideas, D&C concepts, they've been around, just not for climate change.
Exactly. The study mentions older uses, like purifying air in submarines or spacecraft, or in some industrial gas separation processes, tiny scale compared to what we're talking about for the climate.
Right, so climate scale DDIG is really new, early days commercially.
Very much so. We're seeing the first pilot and demonstration plants now.
And this study mentions some of the companies actually building these things, trying to make it work. Who are they looking at?
Yeah, they give some key examples. Carbon Engineering is a big name, working on that high-temperature HTDAC approach, using a liquid solution. Bill Gates is famously one of their backers.
Okay. And their cost targets.
The study notes they've aimed for somewhere in the 75 to 113 euros per ton range, eventually, at large scale.
And on the low temperature, LTD day side.
Climeworks is probably the most visible one this study mentions. They use a solid sorbent, a kind of engineered fiber material. They actually have operational plants, small ones, in Switzerland and Iceland.
Right. I've heard about the Iceland one storing CO2 underground.
Mm-hmm. And they've also talked about similar long-term cost goals, maybe around 75 euros per ton at scale.
Are there others mentioned? Different chemistries, maybe?
Yeah, this study includes a few more. Global Thermostat, another LTDC player using a different type of solid material, and aminopolymer. They've made some claims about potentially very low costs, though the paper is careful to say comparing these early numbers is hard.
Okay.
They also mention antiphysy using potassium carbonate, again, LTDC operating around 8100 C, and hydrocell, which the study notes for having maybe the lowest regeneration temps, down near 70 or 80 C.
So lots of activity, different approaches,
Mm-hmm.
but you said comparing those cost numbers they announce is difficult.
Extremely difficult. And this study really hammers this point home. Every company, every academic paper, they might use different assumptions. What's the price of electricity or gas? How much does financing cost the WACC, weighted average cost of capital? How pure does the CO2 need to be? How many hours a year does the plant actually run the full load hours, or FLH? All these things massively affect the final cost per ton.
So you can't just take company X's number and compare it to company Y's.
Not directly, no. It's apples and oranges often.
Which is where this study's main contribution comes in, right? They try to level the playing field.
Exactly. They did their own calculations. They took the available technical data and cost estimates for these different systems and recalculated the costs using a standardized set of assumptions.
Like what?
Like assuming a consistent 7% WACC for financing, specific prices for electricity and heat, and importantly, assuming all plants run for, say, 8,000 hours a year, which is almost continuously, just for a baseline comparison.
Yeah. Okay, so applying that standardized lens, what did their analysis show for costs back around 2020 based on what was known then?
Well, based on their recalculations, the costs were still pretty high. For the high-temperature DI models they looked at, including a version based on Carbon Engineering's work but assuming electric heating, their standardized cost came out around 186 euros per ton.
Okay, 186 euros, and for the low-temperature systems.
Those generally came out lower in their 2020 snapshot. For example, the Antimussi model recalculated to about 155 euros per ton. Another approach they analyzed, based on Klaus Lackner's work using moisture swing adsorption, came in closer to 99 euros per ton in their standardized model.
So even back in 2020, this study's standardized comparison suggested LT-Day might have a cost edge.
That was their finding, yes. Primarily because of those lower heat needs and, critically, the potential to use lower-grade, cheaper heat sources, maybe even waste heat from other processes, which just isn't hot enough for the HT systems.
Okay, but those numbers, even the lowest around 100 euro, still sound pretty expensive if you need to capture billions of tons.
Mm-hmm.
Where does the hope come from? Scaling up.
Exactly. This is where the projections get really interesting. This study uses learning curves to forecast future costs.
The idea that things get cheaper the more you build them.
Precisely. Like we saw with solar panels, wind turbines, batteries. As the total installed capacity of these grows worldwide, The cost to build the next plant should fall. You get better at manufacturing, supply chains improve, the tech gets tweaked. You learn by doing.
And the scale needed for DD is enormous.
Huge. This study estimates that by 2050, the global demand for DC capacity could be massive, potentially up to 15 gigatons, 15 billion tons per year. A lot of that would be for that active CO2 removal we talked about.
And building that much capacity is what drives the costs down in their model.
That's the engine of the cost reduction, yes.
Did they model different speeds of that rollout?
They did. Two main scenarios. A conservative scenario, or CS, where maybe only half that projected capacity gets built, and the learning rate is 10% drop 10% for every doubling of capacity.
Okay. And the other?
Their base case scenario, or BS. This assumes we actually build 100% of the projected need, and the learning rate is faster at 15%. They argue this 15% might be more realistic for DS because it's potentially quite modular, like batteries or electrolyzers, which have shown similar or even faster learning rates.
Right, you can maybe mass produce the units.
Right.
So what cost ranges did they project for 2050 under those scenarios? This is the key number, isn't it?
It really is. And the projections are striking. For LTDs, assuming that 8,000 hours runtime and 7% WACC.
Yeah.
By 2050, they project costs could fall to between 54 euros per ton in that conservative scenario, down to maybe 38 euros per ton in the base case scenario.
38 euros. That's getting into a much more feasible range.
It is. A huge drop from those 2020 estimates. For HTDAC, the projected 2050 costs were a bit higher in this study, ranging from 71 euros down to 54 euros per ton across the two scenarios.
So LTDAC maintains that potential cost advantage in their projections.
It does. And they highlight something crucial for LTDC, if you can get access to free waste heat.
Ah, like from a nearby factory or data center.
Exactly. If that low temperature heat is essentially free, their 2050 base case projection for LTDC drops even further, down to around 32 euros per ton.
Wow, okay, so finding those synergies, co-locating LTDC with sources of waste heat could be incredibly important for lowering costs.
Hugely important. It really changes the economics.
And this study, they did a sensitivity analysis too, looking at what factors swing the cost the most.
Yes, figure 8 in the paper breaks that down. It shows the final cost, the levelized cost of CO2 capture, or LCI. It's really sensitive to a few key things.
Like
the cost of financing, that WACC number, is a big one. So is the initial capital cost of the equipment, the CapEx, and crucially, energy costs.
Which energy cost matters most depends on the type, right?
Exactly. For HTDAC, electricity price is a major driver because it uses more electricity. For LTDAC, it's the cost of that heat supply. Getting cheap heat is paramount. And how many hours the plant runs per year? The FLH, that also makes a big difference. More hours means spreading the capital cost over more tons of CO2.
Makes sense. Cheap renewables, cheap financing, run it constantly. That's the path to low cost.
That's the recipe.
Okay, beyond the capture cost itself, this study also considers other practical aspects. Land use is one people always ask about. Are these things going to cover the planet?
It's a fair question. The study looks at this. The actual active area where the air contact happens, yes, it adds up if you need gigatons of capture. The paper quotes numbers like maybe 25 square kilometers of active area per million tons of CO2 per year for some designs.
That sounds like a lot.
It does, but the study points out that the total footprint depends on how you deploy it. You don't build one giant square, you spread out modules, and the space between the modules could potentially be used for other things, like solar panels, maybe. They cite other estimates suggesting the overall footprint might be much smaller in practice, like maybe 1.5 square kilometers for a 1,000,000-ton per year plant, or even less, like 0.4 square kilometers per million tons if it's highly distributed, according to a Climeworks estimate they mentioned. So significant, yes, but maybe manageable.
Okay, perhaps not as land intensive as feared, especially if spread out. What about water? Does DAE use a lot of water?
Again, it depends. HT-DAC, the high-temperature liquid systems, they can be quite water-intensive. This study mentions a carbon engineering design needing maybe 4.7 tons of water makeup per ton of CO2 captured, mostly due to evaporation.
So you probably wouldn't build those in a desert.
Exactly. The paper estimates water costs could add, 3 to 8 euros per ton in water-stressed places. It's a real siting constraint.
But LT today is different here too.
Often, yes. A really interesting point the study makes is that some LTDC systems, like those from Climeworks or Hydrocell they mentioned, can actually capture water from the air, sometimes more water than they consume.
So they could be net water producers.
Potentially, yes. which is a neat advantage, especially if you want to use the CO2 for something downstream that needs water, like making hydrogen fuel through electrolysis.
Right, that synergy again. Okay, so you've captured the CO2, you still need to deal with it. Compress it, move it, store it. That adds costs, too.
Absolutely. This study accounts for that. Compressing the CO2 to pipeline pressure, say 150 bar, takes a fair bit of energy, around 132 kilowatt hours of electricity per ton.
And transport.
Depends how far and how much. Pipelines are usually cheapest for large volumes over land. The study gives a range of maybe 1.5 to over 40 euros per ton, depending on the scale and distance. Shipping by boat is maybe 11 to 20 euros per ton. Trucks and trains for smaller amounts are options too, but likely pricier per ton.
And then the final step, putting it away permanently.
Yeah, geological storage, usually deep underground in porous rock formations like saline aquifers. This study uses a benchmark cost of around 10 euros per ton for good storage sites. The key is ensuring it's permanent or using the CO2 in a way that locks it up, like in building materials through mineral carbonation.
Okay, this brings us to a really important comparison this study makes. DC versus that point source capture, PSCC, we talked about earlier. PSCC is generally cheaper now because the CO2 is concentrated at the source.
That's conventional wisdom, yes. Grabbing 15% CO2 from a smokestack is easier than grabbing 0.04% from thin air.
So how does this study see that comparison evolving? They have a chart on this, right?
They do. Figure 10. It's really insightful. It plots their projected DC costs for 2040 and 2050 against the current and projected costs for PSCC in different industries. Power plants, cement, steel, etc.
And the takeaway, will D ever compete on cost?
According to this study's analysis, yes, it looks like it will. Their projections show large-scale DC costs coming down significantly, becoming competitive first with the more expensive forms of PSCC. Yeah. Potentially with the mid-range costs and maybe even the lower range of PSCC costs, especially if that LTD gets access to cheap or free waste heat. The cost gap is projected to narrow dramatically.
So by mid-century, capturing from air might not be much more expensive than capturing from some industrial sources.
That's what this study suggests is possible with scale and learning. And they make another smart point. Comparing just the capture cost might be too simplistic.
How so?
Well, PSCC on a fossil fuel plant still leaves some emissions, right? And you might face carbon taxes on those later. Plus, the fossil fuel itself has upstream emissions. DSE, powered by renewables and coupled with storage, gives you true net negative emissions. So the full system value proposition for DSE could be stronger, even if the headline capture cost is similar.
Right, it's about achieving actual removal, not just slightly less emission.
Exactly. Plus, the location factor. PSCC has to be where the factory or power plant is. DC can be built where renewable energy is cheapest, or right next to the best CO2 storage sites, or near where CO2 is needed for utilization. That flexibility is huge.
This study also gives a concrete example of how DT could plug into future energy systems, looking at power to gas.
Yeah, this is a great case study they include. Power to gas, or PTG, is where you use electricity, ideally renewable electricity, to split water into hydrogen via electrolysis.
All right.
Then you take that hydrogen and react it with CO2 to create synthetic methane, basically synthetic natural gas, SNG, which you can then use in existing gas pipelines or for fuel.
And DT provides the C in the SNG.
Precisely. It's the carbon source. And this study specifically looks at integrating LTDC with PTG systems.
And leveraging that waste heat again.
You got it. Both the electrolyzer making the hydrogen and the methanation reactor making the SNG produce heat. This study analyzes how that waste heat, which is typically low temperature, could potentially provide the heat needed for the LTDD process, making the whole thing more integrated and efficient.
Makes sense. How does doing that integration affect the final cost of the synthetic gas?
It's an interesting trade-off they explore. You want to run the dock unit as much as possible, high full load hours, to bring down the cost per ton of CO2, the L side.
Right. Spread the capital cost.
But the PTG part, the electrolyzer and methanator, might run fewer hours, maybe only when renewable electricity is really cheap. If you force the PTG to run more hours just to match the dock, its electricity costs might go up, increasing the overall cost of the synthetic gas, the LCUD.
So optimizing the dock cost doesn't automatically optimize the final fuel cost if they're tightly coupled.
Exactly. Figure 11 in the paper shows this dynamic. Sometimes slightly more expensive CO2 from a less utilized dock might lead to cheaper overall SNG if the PTG part can run more optimally.
So the CO2 cost is just one part of the final S&G price tag.
For sure. Figure 12 breaks down the S&G cost. Initially, say in 2020, the CO2 from DOC makes up a pretty big chunk, maybe 27% of the total S&G cost in their model.
But that share shrinks over time.
Dramatically. As those DA costs fall towards 2050, the CO2 becomes a much smaller fraction of the S&G cost. Electricity for the electrolysis becomes the dominant cost driver. This study actually suggests that decoupling the systems might be best.
Meaning?
Run the DA plant flat out at high capacity to get the cheapest CO2. Store that CO2 temporarily, then run the PTG plant whenever it makes most sense economically, using the stored CO2. That way you potentially get the lowest cost for both the CO2 and the final synthetic gas.
Interesting. So flexibility in operation is key there too.
Seems to be.
Okay, so stepping back, this deep dive into the techno-economic assessment of CO2 direct air capture plants study, it really paints a picture of a technology that, yes, is expensive now, but it has a clear pathway to becoming much more affordable.
It really does. It reinforces that DAKIS is likely a necessary tool, not just optional, for hitting net zero and especially net negative goals. We need it alongside emission cuts.
And this study specifically suggests that low-temperature day, particularly if it can tap into waste heat, looks quite promising from a cost perspective, with potential to get significantly cheaper by 2050.
Yeah, those projected costs down in the, 30s or 40s or 50s per ton range.
Yeah.
That's achievable if we see massive global deployment, those learning curves kick in, and critically, if we have abundant, cheap renewable energy and waste heat sources.
It's not just about the capture device itself, it's the whole system, energy, finance, policy.
Absolutely.
So this study provides a cautiously optimistic outlook. The tech is developing, the costs can come down, making D potentially affordable and competitive, a vital complement to point source capture.
The pathway's there in the analysis. The question is whether we'll build it out fast enough.
Which really leads us to the final thought, stemming directly from this study's findings. The techno-economics suggest large-scale DDATS is becoming feasible, maybe even affordable within a few decades. But realizing the potential hinges massively on investment, market creation, and supportive policies. Given DAS's unique power to actually remove CO2 from the atmosphere, how quickly will the world mobilize the resources and political will to make it happen at scale?
That's the multi-trillion-dollar question, isn't it? Hanging in the air.
Indeed. A very apt place to end our deep dive today on the techno-economic assessment of CO2 direct air capture plants.